question is, what is the most important discovery in all of physics? Okay. Granted, your answer may depend on your own personal taste, but today I'd like to make the case for something you learned way back as a kid in 6th grade science class. Now this should be something you recognize. This is a model of an atom, the basic building block for all matter in the universe. Everything you can taste, touch, and smell, everything from the largest star to the smallest grain of sand is made up of trillions and trillions and trillions of atoms. You're told in school that at the center of every atom lies a positively charged bundle, a nucleus of protons and neutrons. The number of protons determines the elemental type. So a lighter element like helium will have fewer protons than a heavier element like lead. And orbiting around this nucleus, like little planets orbiting a little sun, are the negatively charged ball-like electrons. Okay, just a fraction of the proton mass, and so tiny they really take up no space at all. It is these blue dots that shape our world. Because without the electrons to balance charge inside of nuclei sitting side by side, atoms would repel each other in opposite directions. Electrons hold atoms together. Okay. Without them, all solid objects, the walls, the chairs, me, you, simply wouldn't exist. My name is Max. I work in the physics department at Northwestern University. When I talk about electrons, I do still feel a bit like a kid, because electrons, responsible for atomic and molecular bonding, are the foundation of chemistry. And electrons, which determine how RNA and DNA fold and interact in our cells, is the very heart of biology. Okay, if you're sitting there though, and you're shrugging, and you say, okay, that's neat about science, Max, but I'm not a scientist. What has an electron ever done for me? Well, then I point you to this picture from 1947. This attempt at abstract art is actually the world's greatest invention. This is humankind wielding the power of the electron. This essentially is the earliest caveman drawing we have in the age of the computer. Physicists found that if they fed a few electrons into the center of this crystal, they could cause a sudden avalanche of electrons to move spontaneously across the crystal, charring that cylinder black in the process. Okay, they could turn this avalanche on and off simply by adding or removing a few electrons. And over the years, we've honed this device. We've shrunk this technology, this electron switch, smaller and smaller. It's so small now we need only a single electron to flip the switch. It's so small that 8.5 billion of these transistors now fit inside of your pocket. I mean, the only reason your phone works at all is because there's 8.5 billion electron switches all working together, moving electrons back and forth at lightning speed, connect you to your friends via text, or let you download a picture, or connect you to the internet. But I'm not here to talk about smartphones. I'm going to let you in on a little secret. Okay, that atomic model we were all taught in class is in fact a lie. I know. Actually, it didn't even come remotely close to capturing true nature, whose reality is even more impressive than we could have ever imagined. Because this is what an atom really looks like. And the truth is, electrons are much, much weirder than you think. They behave in strange and unintuitive ways, and they do things that seem impossible. They do this because they're not governed by the physics of the everyday world, but by the physics of the ultra-small, the nanoscale physics, the physics of quantum mechanics. Okay, to convey just how seemingly illogical this quantum world is, let me give you a few examples of real quantum effects. So imagine an electron about the size of a bouncy ball in my hand. I can drop the ball, bounce off the ground, and catch it. I can even throw it, bounce a little higher, and I can catch it again. Okay, but according to quantum mechanics, I can throw this ball so hard that it disappears. It phases right to the floor and continues on its path, unimpeded, directly into the basement below. Now imagine I go out into the lake fill, toss it into the water. The ball hits the water, sinks to the bottom, creates a splash, and in its wake, ripples slowly spread. I can walk up to the shore, lean over, and touch a wave as it reaches my feet. And suddenly, all the ripples disappear, and right where I wet my finger, out pops the ball. Okay, to be clear, although we don't observe these phenomena in everyday life, well, electrons living in the quantum realm experience these things constantly. And when it was discovered, the true nature of super small objects like the electron baffled scientists. We had to completely rework our understanding of how the world functions. And to this day, quantum mechanics continues to keep physicists on their feet. Okay? It's not all bad though, don't panic. Because we now know just enough quantum mechanics to begin to harness the electron's full potential inside something we call a quantum computer. And I'll warn you, a computer built on the bizarre physics of quantum mechanics may look a little bit unconventional. Indeed, the computer I'm helping to build looks less like a laptop desktop and more like a chandelier I ripped straight from the Art Institute. Okay, this technology is new. It's so new, in fact, we're not exactly sure what it's capable of. But a few years ago, a quantum computer just like this one was able to solve a complex factorization problem in 3 minutes. It was estimated that if that problem was given to the world's most powerful supercomputer, it would have taken it over 10,000 years to solve. With the type of processing power afforded to us by quantum computing, we hope to simulate nature in order to understand nature. For the first time ever, we can use a computer to replicate atoms and molecules inside of cells, inside of stars, inside of materials that don't even yet exist. We want to use quantum mechanics to simulate quantum mechanics, and in the process, unravel nature's deepest secrets. And that journey started with the electron. Where, I wonder, will it end?